So, invited speakers, friends, ladies and gentlemen, first allow me to introduce myself. That's what I always do. I think you should have a right to know who I am. I'm Svante Bolin. I'm the chairman of the Swedish Meteorological Society and one of the organizers of this seminar. So it's a great pleasure and a bit overwhelming to see all of you here and sense the strong interest in a thing that is worrying us very much and is a very challenging issue at the same time. The destiny of planet Earth, and in particular the fate of the oceans and the cryosphere in climate change. This event focuses on the very recently released report by the Intergovernmental Panel on Climate Change, IPCC. And the special report is named The Ocean and Cryosphere in the Changing Climate. But allow me to spend a couple of minutes reminding you about the achievements of the IPCC, not the least receiving the Nobel Peace Prize in 2007. But the IPCC was established in November 1988 on the initiative of two organizations, the United Nations Environment Programme, UNEP, under its director Tolba, and the World Meteorological Organization, WMO, under its head Dr. Obasi. Professor Bert Bolin became the first chairman of the IPCC, and he stayed on for 10 years as such. Bert Bolin was a professor here at the Stockholm University, as you very well know, I think, and has given name to the Bolin Center for Climatic Research. So, of course, in honor of his contributions to climate science and the international community. But more importantly for me, he was also my professor. So he was my thesis advisor when I then took my PhD here at Stockholm University. I entered the work of IPCC already in May 1989 when I participated in the second meeting of the IPCC in Nairobi, after just having started my job as head of the new Climate and Air Pollution Division of the Ministry of Environment and Energy in Sweden. At that meeting, I had been given instructions as head of the Swedish delegation to invite the IPCC to hold its first assessment meeting in Sweden. And I don't know if there are many here that remember that. That meeting took place in 1990. The first assessment report was adopted at that meeting that took place in Sundsvall on the last day of August in 1990, with Bert Bolin as the chairman and me as the organizer of the meeting on behalf of the Swedish government. The first assessment provided the first comprehensive treatment of all aspects of climate change known at that time. The report of Working Group 3 even contained, as an annex, a blueprint for an international agreement on climate change. So that was already on the table when negotiations started. In the so-called overview of the 1990 report, the IPCC stated, the observed increase could be largely due to natural variability. Alternatively, this variability and other human factors could have offset the still larger human-induced greenhouse warming. The unequivocal detection of the enhanced greenhouse effect from observation is not likely for a decade or more. And that was turned out later a very correct statement. But now there are no doubts. It may be interesting to contrast that to the one of the key statements of AR5 from 2014. Warming of the climate system is unequivocal, and since the 1950s, many of the observed changes are unprecedented over decades to millennia. The atmosphere and the ocean have warmed, the amounts of snow and ice have diminished, and sea level has risen. So it's another world we are living in now as compared to 1990. IPCC's first assessment report led to the Framework Convention on Climate Change after a decision by the UN General Assembly in December 1990. And the AR5 was the basis for the Paris Agreement with its 2 degrees goal. Since AR5, IPCC has published several special reports, one on global warming of 1.5 degrees that we presented here last year. That one was requested by the UNFCCC, by the way. This autumn, 2 further reports have been presented. The first out was Climate Change and Land, and a couple of months ago. And the second one is the Ocean and Cryosphere in Changing Climate, which is then the focus of our deliberations here today. Both are valuable contributions to our understanding of what happens in the different compartments of the Earth, land, oceans, and everything frozen. So today we are focusing on the oceans and the cryosphere. The polar regions and glaciers are all over the world are at great risk to collapse. The temperature is increasing by more than 2 times the global average in the Arctic. Newly discovered instabilities of major ice sheets in the Antarctica implies sea level rise of 3 meters or more by 2300. What happens in the cryosphere and the oceans have worldwide repercussions. So on behalf of the organizers, the Swedish Meteorological Society, the Stockholm University with its Bolin Center and Department of Meteorology, and the Swedish Meteorological and Hydrological Institute, I would like to wish you all very welcome to this afternoon seminar. In fact, this is the 3rd time we have the pleasure of presenting important IPCC reports here at Stockholm University. However, we have to wait until 2021 now until we can do that again, since that is when AR6 will be available for presentation. But today we have a fantastic lineup of speakers. They are sitting here on the front row, and you will hear from them all. The author they have all been actively involved in the writing of the Oceans and Cryosphere report. And then we have also 3 panelists that we have invited to comment on what they have heard about this report, representing the Swedish government, environmental NGOs, and the media representative. We are very happy about that. I will not speak much longer now because we have important things to listen to and not listen to me. I think so. I will cut myself off, but I will give the floor to Nina Kirchner, who is the co-director of the Bolin Center, and after that we go ahead with the real stuff. Thank you very much. So you take this one, yeah.
We do this microphone stuff because it's for the streaming. It's not that you can hear us better if we speak sufficiently loud and clear, but it's for those who follow the streaming. And later also, if you ask questions, we will pass around the microphone for exactly the same reason. So let's see if we can get this going. Yes. So thank you very much for giving me the opportunity to speak to you here. My name is Nina Kirchner. I'm one of the 2 directors of the Bolin Center. And why is there a Bolin Center? We are talking about a report on changing climate. What you see here is a visualization of the changing climate. This visualization is called warming stripes. It has been a lot in the media during the summer. It's to be read like a barcode from left to right. Blue is cold colors and red is warm colors. And this is a warming stripe for Stockholm extending back to 1756. And I think that you can see that it is getting warmer towards the right, which is the present day. If you're not convinced, if you think there is too much red in the left part, here is a warming stripe for the Arctic from Longyearbyen in Svalbard, where you see it very clearly that it is actually getting warmer. And this time series is 118 years long. So because we have this warming climate, we are working with the science connected to it. And in the Bolin Center, we are 3 partners. We are Stockholm University with 6 departments. We are the Royal Institute of Technology, KTH, with a couple of departments, and the Swedish Meteorological and Hydrological Institute. And we are, of course, named after Bert Bolin, who was a professor of meteorology here at Stockholm University. And he was also the founder of the IPCC. If you ever happen to be, especially for our guests from abroad, on the Swedish island of Öland, you can walk the Bolin hiking trail, where we have illustrated Bolin's work for the broader public. So if you're hiking along that nice trail from one side of the island to the other, you can follow Bert Bolin's work and his most important achievements. So today we are here to hear about the newest report on the ocean and cryosphere in the changing climate. We are working a lot with that in the Bolin Center as well. The Bolin Center was founded basically in 2006 when we got a big chunk of money from the government based actually on the very core of what the Bolin Center is today. It was a climate research school back in 2005. We get another big chunk of money in 2010. We grow into an organization that had a couple of different research areas. We had evaluations, of course, as this whole game is played always. And we have also merged with, if you may call it, the green branch of climate, with biodiversity, with landscape changes in 2016, when we grew into 8 research areas. And while this was all sort of constrained or confined to the natural sciences, we extended into the human sciences and social sciences in 2018. And of course, we are looking to an extension into the future. So since the beginning, we have grown into a center that is basically a multidisciplinary consortium of more than 380 scientists in Sweden, who conduct research, graduate education, and outreach related to the Earth's climate. And our mission is to create and to communicate fundamental knowledge about climate and the Earth system as a part of an evolving global effort to understand, mitigate, and adapt to climate change, very much in the spirit of Bert Bolin. And if I still haven't convinced you with the warming stripes, here's another example from Sweden. This is the short period of time where the Bolin Center has been active. But of course, we are concerned about how this is going to be in the future and how we can contribute. We have our 8 research areas. They span basically all components of the climate system. I'm not going to read all these names for you. We have reports that you can find either on our webpage or here in print at the university. And all this research is conducted in these research areas, and the center is organized. These research areas represent the core of our center. We have complementary activities. We have the Climate Research School still following us and carrying us into the future, but we have also extended into a modeling coordination. We have a database where we look after that data is made publicly available, open access for everyone. We have a mentoring program, especially for younger and early career scientists. We have a directorate, a board, we have external science advisors, and so forth. So we have grown from basically from a research school into a full-fledged center. If you want to know more about us, we have our homepage here. You find publications there, you find movies there that we have recorded on occasions like this or others. We have projects that concern services to the stakeholders and the media. We have, for instance, a group that is called Climate Answers by Scientists. We have a climate arena where we work with the business sector. And we have a number of really great events that are regular and forthcoming. We have every year a high-profile lecture, Bert Bolin Climate Lecture, where we invite a distinguished scientist to give this lecture in honor of Bert Bolin. This year it's Professor Maureen Ramo from Lamont Doherty. This lecture will be held in connection with our internal annual conference, the Bolin Days, and then we have mainly outreach activities in each spring of the year. The Climate Festival that we next year for the first time will end with a big event in Kungsträdgården. So this is a really nice opportunity to meet us in person if you do not only want to meet us digitally. There's contact addresses, and this is about everything I had to say about the Bolin Center. Thank you very much for listening. I hope we have an interesting afternoon, and I will hand over to Jonas Nikander now, and you will speak into your handheld microphone. Yes, very good, thank you.
Okay, so thank you, Nina. So now we will start the real program here with the about this report on the cryosphere and the oceans and the polar regions. So I'm Jonas Nikander. I'm a professor here at the Department of Meteorology, and I will be chairing the first session before the coffee break. Yes. And okay. The first speak, I should also mention a few general things here. So each talk we have allotted 25 minutes. So hopefully the speakers will take something like 20 minutes, and then there will be a few minutes for questions after the talks. Yes. Yes, and so I should also say, for those of you who have seen the program before, I mean, everyone could get the program here. For those of you who have seen the previously announced program, there are a couple of changes. One is that Jochen Hinkel, who was going to talk about impacts, he has been ill. He got noticed yesterday that he was ill, and we have not been able to replace him, so he's out of the program. So one new panelist at the end, Jannike Kihlberg, who was not announced before. And because of this missing talk here, there will be some more questions at the end of all the talks here. So for questions from the audience. So there will be only a few minutes after each talk, but you can think of questions and ask more after the last talk, then there will be some extra time. And with that, I think we can start. And the first speaker here is Marko Romokainen, who is a professor at the University of Lund, a professor of climatology. He's also working with climate issues at the SMHI, the Swedish Met Office. And he's maybe the most interesting point here is that he is the Swedish focal point at the IPCC. That means that he is sort of the contact point between the international IPCC and the Swedish delegation. So please, Marko.
Thank you, Jonas. Can you hear me as well? Yes. About framing and context, because this report came from somewhere. It's part of a bigger assessment cycle or work program of the IPCC, the sixth one. Svante already said a few words about how it all how it all started. But of course, it has continued for now more than 30 years of the IPCC work, the IPCC assessments. The task of the IPCC is to assess the state of knowledge on climate change. It's about the scientific knowledge, about socioeconomic knowledge, about the technical knowledge. Assess at the time in question what literature has been put forth, what we know, and also what we do not know, and how well we know what we know and how well we know what we do not know. The authors, not least, are very familiar of trying to make this judgment of what is the confidence level, what is the likelihood of an outcome, how far do the results actually take us in understanding and assessing what it's all about. It's an intergovernmental panel, which means that the members of the panel are the countries of the world, 195 states to be more exact. Sweden is a member, United States is a member, Kiribati is a member, and so on and so on. Researchers contribute to the work of the IPCC in working groups and a task force. When it's time to write a report, the researchers get together, they go through the literature, they do the assessment of what the state of the knowledge on climate change is. Researchers also contribute, external researchers, to the working groups as reviewers of the successive drafts of the report. The IPCC is also expected to be relevant to policy. The knowledge should be useful in forming policymakers and policy. But the IPCC is not to prescribe solutions. The IPCC is not to say this must be done or that should be done and so forth. That is up to the next step, the policymakers, politicians, the society at large, to decide what should be done with the knowledge that's available from science and so forth. There's a very rigorous process of actually doing the assessments. It all starts from the discussion between the countries of what kind of report should be written. For example, when the current assessment cycle was decided a few years ago, there were something like 30 suggestions for special reports, of which 3 have come into being. The panel approves the outline. These are the title of the report, these are the sections, here is some ideas of the contents, which then the researchers have ahead of them when they work. There's a nomination of round of authors, a selection of authors, and then the authors start working, going through the literature, writing, assessing. This leads to a first draft, which goes to external review by yet additional scientists and experts. This is a second draft, which goes into the review by external experts and the governments. This is the final draft, and a draft of the summary for policymakers, which is discussed in the same way, and finally discussed between the countries together with the scientists in the final plenary, leading to the summary policymakers and, of course, the full report, as is now the case with the Oceans and Cryosphere report. The amount of work that the IPCC has done during the past 30 years is extensive. There have been 5 assessment cycles before this 6th one, and all have led into a number of thick reports on the physical science, on the climate change, on vulnerability, adaptation impacts, and mitigation, what to do about climate, that we are affecting climate. 1990, 95, 2001, 2007, 2013, 14, every 6 to 7 years. There have been 11 special reports before this one, so now the number is 12, looking more focused on something like climate change and aviation, or carbon capture and storage, or renewable energy, or extreme events, or the ocean and the cryosphere. There are also technical papers, there's methodology reports, there's a very rich selection of literature and assessment available from the IPCC, can be found on the homepage. The 6th assessment cycle, which has now been going on for a few years, contains 3 special reports. 1.5 degree global warming was finalized about a year ago in October 2018. Climate change and land from this August. The present report, the ocean and cryosphere and changing climate, about a month old. Has also been an update on the guidelines for greenhouse gas inventories. It's very technical how the country should sort of monitor and report of emissions. And then the main report, which will come in 2021, and the synthesis of the 6th assessment cycle in 2022. I could mention that for those interested, the first draft of the second part of the main report is now out for the first external review round. So you can go to the SMHI homepage or the IPCC homepage if you are interested to learn more about the process and perhaps participating. The process in numbers, if you like, on this special report, the ocean and the cryosphere, it was written by 104 authors or authors and review editors. The latter followed the process, and they came from 36 countries of the world. Although 36 countries, 19 were developing countries or so-called economies in transition. The authors, well, you know it better than I do, waded through 6,981 scientific publications, and I'm sure they read a number of additional ones. The external review rounds gathered comments from 1,851 reviewers, and they together provided the process with 31,176 review comments, each one of which was read, commented on, responded, and will be documented on the IPCC homepage. I've done that as well in my earlier life. About the report, I'm not going to tell anything about the results, obviously, but it does go through the knowledge on which changes have already been observed in the ocean and cryosphere systems. The oceans, the cryospheres, the snow cover, glaciers, ice sheets, sea ice, permafrost, and so forth. And also what kind of impacts and consequences have been observed related to these changes in the ocean and the cryosphere. The report also goes through the projected, calculated, possible future changes in the ocean and the cryosphere, and the impacts and consequences of these projected future changes. And it also outlines the challenges that this presents to us, and also possible response options which we could do about this to handle the changes and combat the change as well. So it is about the natural sciences part of it, if you like. It's about the social sciences, humanities, technical part of it, if you like. It's going from here to here. Finally, we're good at what next. You get this summary for policymakers, about 30 pages. You can also access the full report with a few hundred pages, and you can read it and then think, well, and then what happens? And of course, the reports by the IPCC are available to everyone in the global society. They can be read and discussed and debated and used as information for discussions, decisions, and so forth, on all levels, from the international level to national level to the subnational level in the industries, in the civil society, and so forth. But of course, perhaps the main task of the IPCC is to provide policymakers the scientific information, the science or the assessment of knowledge that can be used when decisions are formulated, discussed, and taken. And in this case, as we all know, that oceans will be most likely heavily lifted forth in the next round of UN climate negotiations in December, it is extremely likely, to use the language of the IPCC, that the results of this special report will also be heavily used, displayed, and discussed in conjunction of the meeting and discussions there. Thank you.
So we'll have a few minutes for that. Okay. So if not, we can go on to the next speaker. So now it's you. So I'm grateful to have here Professor Julien Struve. Oh, I don't know about the pronunciation actually. Struve.
Yeah.
Okay. Yeah. And Professor Struve, she's a professor of polar observations and modeling at the University College London, and also now sharing this with another position in the University of Manitoba in Canada for a number of years ahead. And she is working in particular with the interaction between atmosphere and sea ice, and remote sensing and predictability of sea ice, especially in the Arctic and the polar regions. Also, she has done work on the impacts, for instance, on indigenous peoples of the climate change in the Arctic. And one reason that you're here, apart from all this, is that you're also a contributing author of Chapter 3 about polar regions in this SROC report that is the subject of today's seminar here. So, please.
Thank you. How do I find my presentation? Oops, just go. Oh, let's see. Okay, there we go. Yeah, so I was, it's not up there?
Oh, no, okay.
There we go. Oh, no, that's okay. Thanks. Yeah, so I was one of the contributing authors in regards to the sea ice that was written in the SROC report. So I'm going to present a bit on that, as well as the oceans in general. And of course, one of the reasons why we're here is that we know that the polar regions are experiencing quite dramatic changes as a response to a warming planet. But this warming and the responses are not equal in both polar regions. So, for example, in the Arctic, we know that temperatures are warming more than twice as fast as the rest of the planet. And this will have different implications on society and ecosystems and say the changes that we're seeing in the Antarctic. And one of the reasons why we focus on the oceans in this report, as well as the cryosphere in general, is we know that oceans are a key player in regulating climate by absorbing about 90% of the excess heat in the atmosphere, and also absorbing about 1/3 of the CO2 that we put into the atmosphere. And of course, that will lead to ocean acidification. I'm not going to focus on that part in my talk because I think that will come out in the impacts later this afternoon. But I will talk a bit about how the oceans are changing, and of course, sea ice floats on top of the ocean. And most of my work is always focused on what's happening with the sea ice. And sea ice is very important as well because it reflects most of the sun's energy back out to space. So if we start losing that sea ice, we're going to start absorbing the heat in our oceans that will warm even faster, which will further amplify the warming that our planet is going under. I'm sorry that things are cut off. I'm just noticing that. So we might have some slides that are a bit cut off here, but hopefully not too bad. So I'm going to start with just talking about some of our observed changes that we've seen that were discussed in the SROC, and yeah, the top is cut off as well. Sorry about that. So we'll just start with our sea ice record, and we have about 40 years of very good observations now from satellites, and what that has allowed us to do has been to document how quickly Arctic sea ice has been disappearing. And this is a very iconic graph that you've probably seen many times, which is just showing the September sea ice extent from 1979 now through 2019. And we can see that this September pretty much fell right along our long-term trend line. It was the third lowest that we've seen in the satellite data record, followed of course by 2012, which was our record lowest, and also 2007, which were quite unusual and really linked to extreme events. And when we talk about climate change, we're really concerned about this long-term trend line, not so much the departures from that, which are usually a result of extreme weather events. So in the SROC report, there's a statement that says between 1979 and 2018, these September sea ice reductions are very likely to have been on the order of about 12.8 plus or minus 2.3% per decade. If we were to extend this now through 2019, it's gone up slightly, but I think we can pretty safely say that we've been losing about 13% per decade. And this is regardless of what sort of algorithm you apply to the satellite data record to monitor changes in the sea ice. So we've had a lot of attention on the summertime, but it's not just summer where we're seeing these changes. And this is kind of like the temperature curtain. Now we have it for the sea ice. And this is just looking at the departures from average conditions from 1979 through present by year on the x-axis and month on the y-axis. And basically, you can kind of see around the mid-2000s, we started seeing every month of a year where we saw sea ice departures below average conditions. And it wasn't just summer anymore. And then since about 2016, we've had pretty much every month in the Arctic Ocean has seen sea ice departures from average that were more than 2 standard deviations below the long-term average. And the largest departures, well, September 2012 was quite unique. The largest departures from average conditions have actually happened in May and November of 2016. So it's actually kind of outside of the summer melt season. And this is important because it sort of impacts on changes in seasonality that are happening in the Arctic. And so again, with the SROC, they say that it's very likely that Arctic sea ice continues to decline in all months of the year. I would agree with that. I would say it's probably virtually certain, but they say very likely. Where there's a little bit more uncertainty is whether or not these changes have been unprecedented in at least the last 1,000 years. And it's been hard to reconstruct how much sea ice there has been over long time periods, but we're pretty confident that at least for the last 1,000 years, these changes are quite unprecedented. The other thing that's been happening in the Arctic Ocean in particular is that we're losing all the old thick ice. And this is one of the reasons why we are starting to have low ice conditions every summer, is because we're transitioning from an Arctic Ocean that was dominated by thick multi-year ice to one that is now dominated by thinner first-year ice. And one way we can do this with satellite is we can track all the ice parcels as they move around the Arctic Ocean. If they don't melt out and they age another year, then they can assign another age class. And so the red areas are ice that was at least 4 years or older within the Arctic Basin. And then we can contrast that with back this last April, where you can see the red areas have decreased quite a bit. And basically, we've lost about 90% of this 5-year-old plus ice. And we have very high confidence in that. What we don't have is similarly long-term data records on how thick that ice is. But we do know that first-year ice grows about 1.5 to 2 meters thick over time, whereas the older ice has more chances to dynamically thicken and also thermodynamically grow more ice. So these also reflect changes in the thickness of the ice. And so we're virtually certain, if we use the SROC language, that the Arctic sea ice is thinned concurrent with this shift towards a younger ice. The other thing I wanted to draw attention to in terms of a sea ice is that the melt season is getting longer. And again, with the same satellite data that we can map how much ice is there, we can also see how changes are happening in terms of the timing of when melt starts and the timing of when things freeze up. Now, in terms of the melt onset, the trends are much smaller. We're not seeing a dramatic shift necessarily to when the melt season starts. It's a bit earlier for sure in the Barents Sea sector and along the margins of large parts of the marginal seas. but the real changes are actually happening in the freeze up. And so if we look at the freeze up trends, you're looking at 20 to 30 days per decade later freeze up in the Arctic Ocean today than there used to be. And this is since 1979. And the SROC report says there's high confidence that the melt season has extended. Curiously, they say by 3 days per decade since 1979. I don't have as much confidence in the exact number. I would agree that yes, it is extending. How many days on average for the whole Arctic, I think, is a little bit less highly confident, only because of the methods used to detect this. But these changes are also very consistent with what we see if we want to look now at warming of the sea surface temperatures in the Arctic Ocean. And now this figure is from the SROC report, and it shows that in wintertime, so if you look at September, sea surface trends are pretty much positive most everywhere in the Atlantic sector for sure. There's some slight cooling in the Pacific sector. But if we then turn to summer, we see really large positive temperature trends in sea surface temperatures. And this largely reflects then our delays in freeze up, because the ocean cannot freeze again in the wintertime until all that heat that's been gained in that summer mix layer goes back up to the atmosphere. And so again, looking at the language that we have in the SROC, we know that there's high confidence that the Arctic Ocean has warmed. There's a warming of about 0.5 degrees Celsius per decade within the central Arctic Ocean, directly tied to where ice used to be, which is now gone. And so now the mixed layer temperatures have been warming up in the Arctic Ocean. Finally, the last thing I wanted to mention about the oceans in the Arctic is we've also been seeing this freshening of the Arctic Ocean. So we're seeing a freshwater accumulations, particularly in the Beaufort Gyre, where the freshwater has increased by about 40% from 2003 to 2017. And this has happened while we've been losing freshwater in the East Siberian, Laptev, Chukchi, Kara-Barents Seas. So all of the marginal seas around the Arctic Ocean have actually been decreasing their freshwater content, and it's all been accumulating in the Beaufort Gyre. This has medium confidence. It's been assessed in many different ways. Part of the problem is, of course, being able to measure this quite accurately, but changes in sea surface heights are very confirming that this freshwater layer is getting thicker over time. They've also documented positive trends in the freshwater flux to the Bering Strait. Surprisingly, in the report, there's no discussion about the freshwater flux out of Fram Strait. I think part of that might be because there's a lot of uncertainty depending on how you make those observations. And a lot of it has to do with our volume flux and the ice thickness in the Fram Strait. Okay, so switching to the Antarctic, excuse me. Here things are quite different when we talk about sea ice. And I thought I'd first just show the sea ice trends through 2019 for March and September. And a very different picture emerges. So whereas in the Arctic, we have negative trends all months of the year in all regions of the Arctic Ocean, the same is not true for the Antarctic. It's seasonally dependent, and it's also very regionally dependent. So for example, in March, we see positive trends, for example, in the Weddell Sea, balanced out by negative trends in the Bellinghausen Amundsen and the Ross Seas, for example. Whereas in September, we can see positive trends in the Ross Sea, negative trends in the Weddell Sea. And so we have really compensating regional trends in the Antarctic that are strongly seasonal in their nature. And because of that, we don't think Antarctic sea ice is changing. In fact, we have quite high confidence that there's no real significant trend in Antarctic sea ice extent over the satellite data record. And this has been interesting because for a long time we were talking about a slight positive trend increasing sea ice in the Antarctic. But then in 2016, we had this dramatic drop in the sea ice cover in the Antarctic that has sort of continued. I mean, it's starting to recover a little bit from this kind of dramatic event. But because of that, these trends that we had are no longer statistically significant. And in fact, you can also see that there's a lot of year-to-year variability in the Antarctic sea ice cover. And this really also helps to then impact on what we think drives that, which I will talk about in a moment. Also, when we think about changes in the Southern Ocean temperatures, a different pattern emerges as well than what we saw in the Arctic. So now we see that there's warming pretty much northwards of the Antarctic circumpolar current, but this is contrasted with cooling south of that current. And there's been no real change in the location of the ACC, but we do see warming to the north and cooling to the south. There's also some warming that is happening also along the in March. If we're looking at sort of in the Bellinghausen Sea, some of that warm water is maybe making it up on the ice shelves, which I think Rob will talk about. So we do see some changes. They're not as large as what we see in the Arctic, but we have median confidence that there has been freshening in the upper 100 meters since the 1960s, and that this position of the ACC hasn't really changed. And that's different from the AR5 report, where they did see somewhat of a shift in the position of the ACC, but that is no longer true using more recent data. Where our changes are very dramatic in regards to the Southern Ocean are actually if we're looking at the upper 200 meters of the ocean. And this is where we've seen the strongest warming. There's a nice figure from Soleil's paper in 2018 that shows a change in the ocean heat content in the Southern Hemisphere, integrated through 2,000 meters. And where that is most pronounced is pretty much between about 40 to 50 degrees south. So this is a region where we're seeing a big warming in the Southern Ocean temperatures. And this warming for all the regions south of 30 degrees accounted for 35 to 43% of the global mean heat gain in the upper 200 meters since 1970, and that's assessed at very, very high confidence. And the contribution of that has increased between 45 to 62% if we look at the more recent period from 2005 to 2017. So we know that the Southern Ocean is very important in the global ocean heat uptake. So there's very high confidence in that. And basically 75% of the ocean uptake of excess heat from 1870 to 1995 has been taken up in the Southern Ocean. So then the next thing I wanted to talk about is just attribution of these changes. And it's very different depending on the Northern and the Southern Hemisphere. So for example, in the Arctic, there have been several studies now that have been able to link Arctic sea ice loss to increases in greenhouse gases in the atmosphere. And there's a couple that I'll point out. One, I'm an author on, so that's why I know this paper so well. But basically, we were looking at the links between the observed sea ice in September and how much cumulative CO2 emissions we add to the atmosphere. And you find a very strong linear relationship. On the order of 3 square meters per metric ton of CO2 that you add to the atmosphere, that's how much ice you melt. So if I fly from London to New York, that's equivalent to about 3 square meters of sea ice loss. And this is true also in the climate model. So if we project the models out, we see the same linear relationship, but it's about half of what's observed. So we see a higher sensitivity to this in the observations than in the models. Similarly, we could just look at this as a function of global air temperatures. And so we can look at how we increase our global air temperatures and how that's also very linearly related to sea ice loss, which would be expected because of a relationship between global temperatures and CO2. What is interesting, of course, is that there's a lot of spread. So all of these, the shading is from the climate models, and it gives you a sense of the uncertainty and the estimate for internal variability. So there's a plus or minus 20 years uncertainty when we're looking at our sea ice and how it would respond to warming. But I'm going to come back to this figure because at this figure, which was a paper published by Niederdrunk and Nutz in 2018, suggests that at 1.7 degrees of warming, we are going to see ice-free conditions already emerging in September. And this is a little bit different than what the SROC report says in terms of its confidence and when the Arctic Ocean may go ice-free. So anyways, one of the key messages is that at least half of our observed ice loss is a result of increasing greenhouse gases. This is said as very likely with medium confidence. I'm a bit surprised that it's that conservative in its statement because there's been many publications that support this, and usually it's about 50 to 60% of the ice loss appears to be due to anthropogenic warming, and the other 40 to 50% is natural climate variability. Now, in the Antarctic, that's quite different. And part of the reason why is we don't have a lot of confidence. In fact, we have low confidence in the ability of climate models to reproduce the observed changes. They have not been able to replicate, especially the increase of sea ice in the Ross Sea, for example. And we know there's a lot of natural variability in the Antarctic sea ice. And so we have high confidence that it varies quite a bit from year to year. And because of that, there's been this really weak response so far of the Antarctic sea ice to greenhouse gas forcing compared to the Arctic. And so we have medium confidence in that. I would say, I think that's probably okay to say, because a lot of this is also based on our understanding of how the climate models represent processes. But we do understand that poleward wind changes have really driven the changes that we've seen in the Bellinghausen and Ross seas. There's high confidence of the drivers of that, but we don't know necessarily for sure if ozone depletion explains those changes in the winds. So there's still a little bit of lack of confidence on that aspect. We also don't fully understand what drove the record low conditions in 2016 through 2018. There's been some studies that have published on this, but these low changes have continued. And so there's a bit more uncertainty related to those. In terms of the changes in the Arctic temperatures, there's a few key things that have been happening in terms of sea surface temperatures and just heat content in general. One of them is Atlantification of the Arctic Ocean that you may have heard of, where we've been having these warm pulses in terms of volume flux as well as temperature flux of warm water coming in through the Barents Sea sector. And this warm water is now making it to the surface of the Arctic Ocean, changing the stratification and actually inhibiting ice formation. So that's why we've been calling it Atlantification. Part of this could also be a result of the fact that we've had less sea ice. So we're not melting sea ice in the Barents Sea, especially in the northern part of that Barents Sea anymore, because there's no ice there. And so we're not actually putting that cold freshwater cap on top of the ocean that we normally would always have. So we have medium confidence that we have Atlantification. We've also seen Bering Strait heat inflow has been increasing. There was a study by Rebecca Woodgate showing about 60% increase from 2001 to 2014. This one has lower confidence in part because there's not a lot of observations that this is based on, but the observations that are there do suggest we're getting more heat. And then of course, the warming of the sea surface temperatures is largely also driven, especially in summer, by the fact that we've been losing the sea ice. And so now the ocean is absorbing the sun's heat that normally would be reflected back out to space. And so we have high confidence that the warming in the mixed layer, especially in the summer, is linked to the sea ice loss. And you can kind of see this even today, because today, if I look at where we're tracking at record lowest levels in the Arctic Ocean right now. The other map is our sea surface temperatures as of the 20th of October. And so there's parts, and I'm sorry that the color bar is cut off because none of this is formatted for this computer, but the brown areas are temperatures of 5 degrees Celsius. So of course, you're not going to be forming ice yet until you lose all of that heat. And so that's been a big reason why we have the delay in the freeze up in the Arctic Ocean. And in fact, the report states that likely ocean warming in summer has reduced ice growth by about 25% in the Eurasian and the Canadian basins. Now, this is interesting to me because if we think about the Arctic Ocean, typically once the temperatures would get cold enough in winter, you would form ice again. And it was acted as a negative feedback to our summer ice loss. But now it is suggested that this ocean warming might actually be reducing our total ice growth over winter as well, which would then also feed back on losing more of the summer ice every year. Okay, and then before I go on to future projections, drivers of the seven ocean changes. Now, there's a lot of verbiage in the SROC report about what's going on in the Southern Ocean, and a lot of it does have pretty good confidence of what we understand. So for example, the pattern of warmer temperatures north of the ACC and cooling south of it seems to be largely due to upper ocean overturning circulation and mixing processes. There's high confidence in that, so we think we understand why that is. There also seems to be some confidence that a lot of the multi-decadal warming in the Southern Ocean is a result of greenhouse gases and ozone depletion. There's also medium confidence that the warming on the northern side of the ACC is driven by winds. But there's not a whole lot else that was really said with any high confidence at this point, in part because we lack a lot of the observations that we need to understand all the processes in the Southern Ocean. This is also true in the Arctic Ocean. But overall, we know that the Southern Ocean plays such a huge role in the global ocean heat uptake. And so understanding these processes and what's driving it is really important. And I think there's still more that we can do on that end. So finally, I just want to turn to our future projections. And this is stuff I've been focusing a lot on in my research of late. Just looking at what the climate models show us in regards to sea ice in particular. And especially when I think about the Arctic, this is the plot from a paper of mine that I've just continually updated. So now we got the 2019 value on it, which just shows the observed sea ice record compared to all the different emission scenarios from the CMIP5 model ensembles. And what we found is that typically, because the sea ice seems to track the the modeled sea ice tracks the observed sea ice quite well. We're still a little bit maybe more extreme on that end, but since it tracks us quite well, we have really good confidence that these changes in the reduction of sea ice will continue out into the future, at least and through 2050. All the different emission scenarios sort of give similar pathways or trajectories, if you like. But if we were to really reduce our greenhouse gas emissions, and if we were to try to keep the warming to 2 degrees, so following the RCP 2.6 line, we could maybe keep about 4 million square kilometers of ice in the Arctic Basin. This is what we see today. This is what we have today at the end of summer. So that's what we're looking at in CMIP 5 under trying to keep our warming to 2 degrees, for example. And so as a result, the statements are we have high confidence that the sea ice will continue to decline in the Arctic Ocean. Where I think things were a little strange for me is some statements that came up saying that if we have a 1.5 degree of warming and we keep that going for several years, we're likely going to have sea ice present in 2100. And I'm going to come back to that in just a moment. Also, there was statements that said after 10 years of stabilized warming at 2 degrees Celsius, more frequent ice-free summers are expected, which, yes, I agree with that, but only about 10 to 35%, and that this was likely. Again, I'm going to come back to those two statements because I think those are a bit on the conservative end with regards to Arctic sea ice. In terms of ocean sea surface temperatures, this is a plot from the SROC report, and it's kind of what you would expect. I mean, you have sea ice loss in the Arctic Ocean, so you would expect that sea surface temperatures are going to increase. And so there's high confidence that this Arctic Ocean is going to continue to warm, not the surface and also deeper layers. And there's some medium confidence that the Arctic Ocean will continue to freshen from an intensified hydrological cycle. And this isn't necessarily due to changes in precipitation, probably more a result of changes in river runoff. It's not also likely a change to sea ice melt because we won't really have any sea ice to melt in the summer either. So these will be really driven by river runoff. So I don't study rivers. I think the confidence on that seems a bit high, but it's one of the things that they've mentioned in the SROC report. And finally, with regards to Antarctic sea ice, obviously, because the models aren't reproducing the observed changes that we're seeing in the Antarctic sea ice cover, we have a lot less confidence for what's going to happen in the Antarctic out into the future. All the models do suggest that the Antarctic sea ice is going to be shrinking. It also suggests that it should have been already been seeing that, and we don't see that necessarily. So there's lower confidence that there'll be continued declines, but all the models do show this out into the future. Depending on which emission scenario you take, it will be faster or slower, but it should happen. The models are also suggesting that we should also be warming our oceans more in the Southern Ocean, and it will continue to freshen as well. Again, the confidence on this is low because the models currently are not reproducing some of the ocean mixed layer processes or eddies that play an important role in the Weddell Sea, for example. And so because of this, we just don't have as much confidence in those forecasts. So I just want to talk a little bit about what I think are some of the main misses. And part of this is just due to climate sensitivity. I mean, any of our future projections that we make are based on how well the models can simulate all the relevant processes, and as well as the climate sensitivity that we see in the real world today. And we know, at least in regards to the Arctic, this climate sensitivity has been underestimated. There's been several publications that have shown this. And one way to show it is I come back to this plot that I showed earlier, and I'm sorry that it's cut off. That is really unfortunate. But this line is actually what the CMIP 5 multi-model ensemble mean looks like from the models themselves. Correcting it to match the observations is what gives us our forecast of saying that at 1.7 degrees Celsius, we're going to see Arctic oceans ice-free in September. So the observed sensitivity in these models is smaller than observed, and because of that, you don't see the ice going away as fast as we would do if we were to bias correct it to match the observations. So I think there's some problems there, and I think the paper that came out last year nicely showed that and how you can do the bias correction to forecast what will happen in the future. So Dirk Knotts and I expanded on this in another paper last year, and we basically showed that, and I'm sorry the years are cut off again, at 2 degrees, I mean, if we're looking at 2 degrees, the IPCC report said 10 to 35% chance of ice-free conditions in September at 2 degrees. Well, we get actually, if we just correct everything for what the observed sensitivity is, that you're going to have ice free from August to October at 2 degrees. So I think we're very conservative in our statements regarding how quickly the Arctic Ocean may become ice free, or under what warming, or under how much more CO2 we can add to the atmosphere for when we're going to see these conditions happening. And I think it's important to remember, it's not just summer we're talking about, because we can pick this pathway at 3 degrees, you're already looking at 5 months of ice free conditions in the Arctic Ocean. The other point I'd like to make is a lot of what we're saying in terms of our future projections are very sensitive to the modeling experiment. And I've started looking at CMIP 6 now in terms of Arctic sea ice change. And this is just looking at the historical sea ice extent in the Arctic from 1979 to 1989 compared to 2004 to 2014. And the observations are shown in gray, and we're showing a shading, so giving different estimates based on different methods using the same data set to get the sea ice change from the observations. But in CMIP 3, it got a little bit better in CMIP 5, and then it got even better in CMIP 6. So we're starting to match our observations a bit better as we go on in our modeling experiments. And so how we interpret that to what it means for the future is going to be changing depending on which models that we use that go into these decision making. And just finally, I'd like to just point out, looking at the warming so far in CMIP 6, so the solid colors are from CMIP 6 and the lighter colors are from CMIP 5. And this just shows you what the planet, or what the Arctic, not the planet, what the Arctic will look like under 2 degrees of global warming. And this is done by month, and I'm sorry the months are cut off, but this is November up here. And we're looking at 8 to 9 degrees Celsius of warming if we get to a 2 degree of global warming in the Arctic. So again, if we think back about what we're seeing in the Arctic Ocean, how you have this long delay in freeze up, these really warm sea surface temperatures, this is largely a reflection of this warming of the oceans and the loss of the sea ice that is driving these increasing temperatures. And so, 9 degrees, that's huge change in the Arctic, and that's going to massively impact on permafrost, ecosystem, society that live up in the Arctic. So, and I'll just quickly summarize because I'm running out of time. I think in my opinion, I felt like the report really did a good job summarizing our current state of knowledge and the drivers of change that we're seeing in the Arctic, in the polar regions, in the oceans, and the sea ice. Some of the key messages I found were that the Southern Ocean accounted for about 40% of the total heat gain since 1970. I think that's quite important. And also that Arctic sea ice loss is largely driven by increases in greenhouse gases. I think that's pretty clear and clearly stated in the report. But in regard to the future, I do think that it's still somewhat conservative regarding especially the Arctic sea ice, because I think ice-free conditions are more likely at a lower threshold than what they're talking about in the report. And that by 2 degrees, I would say it's probably likely every year, not just 10 to 35% probability. Also, given that our current and future warming is greater in CMIP 6 and in CMIP 5, a lot of these changes that we've been talking about in this report may happen even faster than expected, or maybe larger in magnitude than expected. And then finally, sorry, it's cut off again, but I think, the report really highlights, how society and ecosystems will function and the impacts of 1.5 versus 2 degrees. But we are currently on a track for 3 degrees at this moment in time. So, we're looking at a pretty grim future. And I'll just put up my final slide, which is just Arctic September sea ice extent. And again, sorry for the cutoff, but the interesting thing is now, this is our RCP 2.6 sort of equivalent scenario, which gives us half the amount of ice now that we saw in CMIP 5. And actually 9 out of the 12 models we've looked at do go ice-free, even under this 2 degree target now. So I think we're looking at quite an intense change in the Arctic. Thanks.
Thank you, Julian. So there is time for maybe one quick question, if someone has something.
Yes, so my name is Tom. So I wonder, there have been some heat waves this summer in Alaska and I think also in the Laptev Sea. Do you know how that will affect? But that's quite a lot of degrees warmer than normal.
Yeah, no, you're right. I know it hit like in the 30s in Anchorage this summer, and there was obviously a lot of forest fires as well. I haven't actually looked at the future projections over land, to be completely honest. I don't really know, but I would imagine the warming is just going to keep extending further overland. Because one of the things that was shown in previous studies was how rapid reductions in sea ice actually extend thousands of kilometers inland in terms of temperature impacts.
Okay, thank you very much. Then we take the next speaker, and I'm pleased to welcome Rob DeConto. So Robert is a professor of geosciences at the University of Massachusetts in Amherst. He is a specialist, particularly on ice sheet modeling in Antarctica, which is important for sea level change, of course. And he's been doing simulations also for paleoclimate over long time scales and also in the future, and proposing a new mechanism called the marine ice cliff instability, which has been widely discussed in publications in Nature a few years ago. And he's also a lead author of the Chapter 4 on sea level rise in this SROC report, and a contributing author to Chapter 3 on the polar regions, and also summary for policymakers in this SROC report. So it's very appropriate to have you as a speaker here today. Please.
Great, thank you. If I can find my so how do I need to find my presentation. I haven't driven a PC for a while.
I don't see the cursor here. Oh, no, yeah, there it is. So,
Perfect.
so let's see if
Right. This part I know. That's great. Thank you. Okay, thank you for inviting me here. I'm going to give an overview of mainly the land ice component that we wrote about in the SROC. And I'll sort of taking a clue from Julian's presentation. I'm going to hint at a few things I think that extend beyond the SROC in areas where I think we need to do a better job, in some places that I think some of the reporting could have been stronger. So you don't need to worry about the details of this figure. It's pulled right out of the SROC report. And it's made to sort of comprehensively in one diagram, just sort of lay out all the different processes that drive sea level change. And one thing that we made a strong effort in this report to remind everyone is that sea level change isn't going to be the same for everyone, regardless of the source or the mechanism that's contributing to the global mean. And we're going to see the implications of that in a few minutes. So in the 20th century, it was about 15 or so centimeters of sea level rise. And it was mainly caused by thermal expansion of the ocean. So the ocean's warming, it's taking up more space. Pretty simple. But something has happened early in the 21st century, and this is a big deal. And it's that the land ice component has taken over. This is what's driving most of sea level rise that we're observing today. And if you look at the numbers in terms of the sizes of the reservoirs, so you see on the top left, it says Greenland ice sheet, roughly 7 meters of sea level equivalent ice locked up in that ice sheet. Mountain glaciers that we're going to talk about for a few minutes, a little less than half a meter. Okay, and then you see the big bad one on the right-hand side, Antarctica. So a huge reservoir of ice, roughly 8 times the sea level potential locked up in Antarctica versus Greenland. And only about 1% of the total land ice potential contribution to sea level in mountain glaciers. Okay, so this is a big important take-home message, I think, and that is that we have more confidence that there is an acceleration in sea level rise. Not the rate, you can't accelerate a rate, but the sea level itself, right, is accelerating. And that's pretty easy to see in the satellite era, right? You don't need to be a statistician to see that's not a straight line. So again, over the 20th century, about 15 centimeters of sea level rise. The current rate now is on the order of more than 3 millimeters per year. Some people are arguing that over roughly the last 5 years, the rate has been closer to 5 millimeters. Okay, that's more than twice the average over the last century. Okay, loss of land ice is now dominating. Anthropogenic forcing, this is fairly straightforward in terms of the thermal expansion component to sea level rise. But now, you know, because of the linkages between the polar amplification that Julian just talked about and surface melt on Greenland, we can say that roughly since the 1970s, it's been anthropogenic forcing that is is where the attribution comes from. Okay, another thing that we're going to look at too toward the end is just what the impact in the short term is on things like extreme sea level events. So the confluence of a high tide, for example, with a tropical or an extratropical cyclone, how often those extreme sea level events are happening is changing. And the projections for 2050, I think, will surprise you. And it's one of the big take-home messages of the report. Okay, so I'm trying to do glaciers justice. I didn't work on this. These are some slides that Regina Hawk, who is the coordinating lead author of the Polar Regions chapter, gave me. She knew I was coming here, and I've been giving other presentations like this all over the world. So Regina and her team looked at the contribution in terms of observations from mountain glaciers, all the places that are in blue. So these are the glaciers outside of the Antarctic and Greenland ice sheets. And what they've seen is that from 2006 to 2015, those are the numbers, about 220 gigatons per year over that period. And you could relate that to a global mean sea level change of about plus 0.6 millimeters per year. So that is substantial, but it's not quite as much as coming from in Greenland over the same period. Okay, now this might surprise you. So we're going to look at Antarctica next. These are the Antarctic numbers. They're about half of Greenland. So today, Antarctica is contributing about half to the total rate of sea level change relative to Greenland. Okay, but if you look at this nice little pie chart that Regina gave me, right, this is really illustrative. Okay, mountain glaciers in Greenland roughly on par in terms of their contributions to sea level, but you can see eventually mountain glaciers are literally going to run out of ice to contribute. And even a really small change in the Antarctic system could be just, you know, dramatically impactful. So a lot of the SROC report focused on Antarctica. Okay. So let's look at the glaciers really quickly in terms of the projections. So the numbers are still big, even though I'm telling you that the reservoir isn't all that big, but on a century sort of time scale, mountain glaciers are going to continue to be a really important contributor to sea level rise. Okay, now in the top bullet where it says, there should be a millimeter there, and I'm sorry that there isn't, but those are in millimeters, 18 versus 36. And you can get a feeling for the likely range around those central estimates in the numbers. So you can see right away that even for mountain glaciers, RCP 2.6 is really different from RCP 8.5. Okay, the implications of this, I mean, that to me, that's pretty remarkable that in a more extreme emission scenario, we're going to lose close to half of the glacial ice around the world by 2100. More than 80% of the small glaciers are going to be gone. And what's really important is that the smaller systems that are really sensitive are probably going to be lost regardless of the emissions trajectory that's followed. Okay, now this is the global, but we can regionalize this, and Regina's been working on this for a long time in trying to get a regional picture of this. RCP RCP 2.6 versus 4.5 versus 8.5. These are now in percentages. Oh, I'm sorry, the last figure was in percentages of the total 2100 versus 2015. These are in percentages also. Okay, so 2.6, 4.5, 8.5, you can see that even under 2.6, Central Europe, low latitudes, the Caucasus, right, are going to really take it on the chin in terms of the total inventory of glaciers. Under RCP 8.5, you can see that everything shifts pretty dramatically over to the right. And you can, pick your favorite region and look to see what's happening. And you can see, again, it's Central Europe, right? That's certainly relevant here. The Caucasus, and you can see Scandinavia is pretty close to the top of that list. And I know that you living here are constantly reading reports about individual glaciers disappearing and being lost. Okay, so we'll put this in a context of what it's going to do to sea level, and again, relative to the big ice sheets. Okay, so again, there's going to be in a 2100 plus sort of timescale perspective, so multi-century, there's a limited contribution to sea level rise the mountain glaciers are going to have. But this is still really, really an important issue. So as the mountain glaciers are being lost, there's going to be an increase in runoff in some places that is going to have influences. It's going to impact things like outburst flood events. It will impact agriculture. It will make some places dangerous to travel. Okay, but eventually, as the glaciers begin to retreat more and more, we'll reach a peak, and then we're going to run out of the seasonal distribution of water supplies in places that are very agriculturally sensitive and rely on that seasonal water supply. This is going to have huge implications for agriculture. It's going to have huge implications on tourism, skiing, ice climbing and mountaineering, things like that for sure, but also more fundamentally things like cultural loss in places, many of which are very under-resourced around the world, places that rely on that runoff for agriculture. Okay, so while glaciers are important, they're going to be critically important to the sea level story as it plays out over the next decades to 2100. You start to go beyond that, and we have to look here to the big ice sheets. So you might not have ever seen plots like this before if you're not really involved in this kind of science. I think you can all recognize the familiar Greenland ice sheet on the top right and Antarctica on the bottom right. Sure, I'll take the long one. Okay, on the left is what you would see if you were looking at the bedrock elevation under that ice, as if you were flying overhead with X-ray vision. Okay, and what you can see is that the edges of a lot of the Greenland ice sheet margin are actually terminating on bedrock on land that's above sea level. And the glacier, the ice sheet itself is in contact with the ocean, but mainly through these relatively narrow fjordal channelized high-speed glaciers like, the iconic Jakobshavn and Helheim Glacier over here and Petermann up here, and this slew of ice streams that are actually reaching the ocean. Antarctica is a really different beast because, number one, right, there's 8 times more ice above flotation to drive sea level rise, but essentially the entire margin is in contact with the ocean, but it's in contact with the ocean in a place where a lot of that bedrock here in blue is way below sea level. So a big fraction, little more than 20 meters of sea level rise equivalent ice volume is in these parts of Antarctica here and here and here, here and here, and over here too to some extent that is sitting on bedrock way below sea level. In some places more than 2 kilometers below sea level. So in essence, a lot of the Antarctic ice sheet margin, sort of in a cartoon view, looks like this, where the really thick ice here that's been accumulating, it's been eroding its bed, the weight of the ice is pushing down on the crust, and what we see in some places is that as you move back away from the ocean into the continental interior, the bedrock actually slopes away from the ocean into the interior of the ice sheet. Okay, the ice is flowing from the interior from left to right in this cartoon out into the ocean. The ocean, the Southern Ocean, is still cold enough that the ice doesn't instantly melt. The ice sheet, as it flows out into the ocean, actually forms an extension of itself that's floating. And these are the ice shelves that rim a lot of Antarctica. The ice shelves are really critical because in places where they bump into things, like on the seafloor, imagine a seamount sort of poking up into the bottom of this thing. The flow is from left to right. If the ice shelf is bumping into something, it's going to provide a back stress that is going to hold back the flow of ice from the interior out into the ocean, okay? So what we've been worried about in my community for years has been really focused on, okay, well, if these ice shelves are providing buttressing, if they're lost, if they're thinned, if they become weak, then we're going to have a faster potential rate of flow out into the ocean. And then what could happen is that if we start to speed up the flow because we lose the ice shelves, the point where the ice is just beginning to float, if we start to lose mass out here, and this is called the grounding line, if we start to lose mass in this column of ice just behind the grounding line, then the grounding line isn't going to be the grounding line anymore because the ice sheet is going to start to float at this point. And so the grounding line will move back. And it turns out that the amount of ice that can flow from left to right through the grounding line toward the ocean is a really strong function of how thick the ice is at the grounding line. So we trigger something, maybe a climate trigger like a warm ocean. We start to thin the ice shelves, the ice flows fast, the ice sheet starts to thin right here, the grounding line starts to move back onto this reverse slope bed, and the flow increases. It's a positive feedback. And this is what has become, it's been coined the so-called marine ice sheet instability, okay? In AR5, we knew about this as being a potential driver of rapid sea level rise, but the treatment of that process in the models was suspect, and the observations weren't really giving us great confidence that that mechanism was at play in Antarctica. Okay. Now, the model results that did go into the projections in the SROC do now account for the physics related to this instability. So in a way, this marine ice sheet instability is driving the projections that we're going to look at. Now, there are other processes and mechanisms that really aren't included in the generation of models that we had available to us in the SROC. These are these iconic satellite images of the Larsen B ice shelf out here on the Antarctic Peninsula in the Antarctic summer of 2002. And what these dark bits that you can see is liquid water. It's meltwater on a big Antarctic ice shelf that's roughly the size of a New England state in the USA, for some perspective. The ice shelf is about 600 meters thick here, back here toward the grounding line. Here's the grounded ice that's flowing, streaming in toward that ice shelf, actually that is keeping the ice shelf there. But that was a really warm summer, and it didn't take long for this to happen. Okay, so the ice shelf broke up, and these glaciers sped up, in some cases by a factor of up to 8 times. Okay, now this is a process that's not necessarily driven by ocean warming. Maybe the ocean warming thinned or made that ice shelf weak, but this is relating what's going on in the Antarctic potentially in the future to surface atmospheric warming, which I think was underappreciated in AR5 and very much a focus of a lot of the language in the SROC report. Okay, now another process is this. Here is, this is actually Helheim Glacier on southeast Greenland. This is a beautiful fjordal glacial system. The ice is streaming out toward the ocean, and there used to be in this fjord a floating extension of the glacier, an ice shelf. It's gone. And what's left behind is a mess of broken up iceberg bits, but the grounding line of Helheim is essentially right at this ice cliff location. And here the ice cliff is about a little more than 90 meters tall. Okay, so we have ice that is all broken up. Ice isn't that strong to begin with. The stresses that are produced in an ice cliff that tall actually influence the breakup of the ice front itself. Same thing goes on at Jakobshavn. Okay, now the glaciers in Antarctica, like this one, This is a schematic of a real glacier, the Thwaites Glacier. Is the Thwaites Glacier, if something like what's happening at Jakobshavn and Helheim were to happen in the future to Thwaites, the glacier would be 120 kilometers wide. Yeah, of course, no problem. That's great. Great. That's the pointer's fun, but this is much, much thicker ice. And if something like this were to happen in some of the Antarctic glaciers, the potential for much taller ice cliffs than what we see on Greenland and much wider, in much wider systems is a possibility, and something that we're trying to get a handle on what the implications for something happening like we see in Jakobshavn and Helheim beginning to be triggered in some of the bigger systems on Antarctica. Okay, so we'll come back to the real implications in how we've tried to actually aggregate projections of the different components of sea level rise. So to do this, you have to take the thermal expansion effects on global mean sea level rise, and we can get that from, in this case, CMIP-5 generation of GCMs that tell us about how fast and by how much the oceans are going to warm. That gives us the thermal expansion. Then we can use the GCM input to say something about when the Mountain Glacier contribution is going to come into play. And then we have to do something for Greenland and Antarctica. Greenland is relatively straightforward relative to the complexities of Antarctica, where we have the ice sheet in contact with the ocean. Greenland, most of the surface melt over the last decade or so in Greenland has been driven not so much by the ice-ocean interactions in the dynamic flow of the glaciers that are channelized and draining the ice sheet, but actually just simply from surface melt. So the summer temperatures are so warm that there's enough surface melt that actually makes it out of the system to the ocean to drive the bulk of Greenland's ice sheet loss. Okay, very different from Antarctica. So again, we can get that from GCM projections for Greenland. Antarctica, because of these ice dynamics, the marine ice sheet instability, the potential that we're going to start to lose ice shelves from atmospheric warming, as well as the ice shelves being attacked from the warming ocean below, makes Antarctica a much more difficult beast to handle in terms of trying to nail down some sensitivity. And that is actually reflected in these plots. So this is the aggregate. So this is in the summary for policymakers figure number 1. And it is the sum, essentially, of the different components that we just talked about here on the left. The top left being ocean warming, Greenland, Antarctica, and the glaciers. So you can see that comparatively, on a 2100 sort of year time scale, roughly 20 centimeters from glaciers in RCP 8.5, which is in the red. RCP 2.6 is always shown in blue here. We can see a little bit smaller contribution from Greenland. In Antarctica, we can see a smaller still central estimate, the red line for Antarctica. But if we look at the distance, and I just want to point this out, between the red line, which is the median estimate or the central estimate, and the top of the likely range, you can see it's actually bigger for Antarctica. So it's clear that the uncertainty is larger for Antarctica, even though the central estimate is smaller. And if this was shown, and this is a really important point, and one of the subtle things that doesn't really come maybe out so clearly in the report, if we were to extend these figures on the left out into the future, you would really see the Antarctic contribution begin to expand in terms of that likely range. Okay, and in this case, the likely range language is referring to the 17 to the 83 percentile in the probability. So that is another sort of subtle thing here, is that I just mentioned that there are processes that we're really not directly addressing and resolving in most of the ice sheet modeling, like the surface meltwater impact on breaking the ice shelves up from the atmospheric side, not just the warming from the warm oceans below. There's that, the so-called hydrofracturing of ice shelves. And in places where you have really thick ice in contact with the ocean that have lost their ice shelves, these marine ice cliffs could trigger very fast mechanical calving of the ice of the ice sheet that could be a very significant driver of sea level rise that, again, is really not reflected here. So there are things that could drive very big numbers for Antarctica that are way above the likely range. And again, that's mainly pertaining to Antarctica. We have better confidence in what we're saying at this point about Greenland and the mountain glaciers. So I think that's something that I really wanted to drive home today. In terms of the global mean estimates, the aggregated numbers are 0.4 meters for RCP 2.6, and you can see about double for RCP 8.5. But that difference, that's dramatic in 2100, that difference expands as we move into the future. Okay, so another, just a couple more points I want to get across here. So these are the global means sea level changes for the RCPs. I'm focusing in here. We compared what we're saying in SROC with the AR5 report. And you can see that in RCP 2.6 and 4.5, we're not saying anything that's really different. It's for RCP 8.5. And again, it's this hint that these instabilities in Antarctica could do something faster than we were thinking about just a few years ago. And again, if we were to show the 95 or the 98 percentile, that would even look different still. So the upper bound now is about 1.1 meters, so about 10% higher than we were thinking at the time of the AR5. Okay, important take-home message, and you can look at this figure yourselves. I won't go into the details. Sea level rise is not going to be felt the same everywhere on the planet. In some places, like right here where we're sitting, the land itself is rising as we're sort of rebounding from the last ice age. The last time there was big ice sitting over Stockholm, that ice is gone. Stockholm is rising, even though sea level is rising. Some places in the world, that post-glacial rebound is happening faster than sea level rise. That might be a good thing. But in other places around the world, the land is going down in response to our recovery from the last ice age. The changes in the ice masses actually influence the Earth's gravitational field and in the pole of rotation. And that has another complicating impact on where sea level rise is greater or less in other regions. Some compounding things happen where I live in Boston, Massachusetts. If you look on any of these plots on the right-hand side for RCP 8.5, you can see that the east coast of the US is a hot spot. It's because the land is going down because of post-glacial rebound and because we feel the effects, because of these gravitational effects of more sea level rise from Antarctica, a place that we are worried actually might be a major contributor in the future. The last piece of science that I'll tell you about is this. So the background sea levels are rising. They're going to continue to rise. They are going to continue to rise regardless of our emissions trajectory. So even a heavily mitigated future in terms of greenhouse gas emissions, we're still going to have ongoing sea level rise. It will be a gradually increase in nuisance flooding in some places. In other places, we're going to start to see a dramatic increase in the frequency or the number of extreme sea level events. So again, the convergence of like a high tide and a storm causing a storm surge. And in fact, in about 50% of the tide gauges around the world that we were able to analyze for this analysis, we found that what is today an extreme sea level event that happens once in 100 years becomes an annual event by 2050. Not 2100, not 2300, but by 2050. And that's regardless of the emission scenario. Okay, now you'd think, okay, so if it's regardless of the emission scenario in the tropics, then maybe we shouldn't worry so much about mitigation. Okay, no, we have to worry about mitigation because what we find is that if we look at RCP 2.6 on the bottom left and RCP 8.5, okay, what we're looking at are increasing red colors that show us once we start getting into these reds, purplish reds, we're starting to get into places that are going to start to feel what used to be a 1 in 100 year event every year. And you can see that those dark red colors and black are mainly limited to the tropics and just into the extratropics in RCP 2.6. If we look at RCP 8.5, it extends well into the mid and high latitudes. So some places around the world, like these in the light green dots versus the dark green dots, we would see a more than 1 decade delay in the onset of this real ramp up in the frequency of these extreme events. Okay, so again, I think that mitigation is, the sea level rise is really one of the main sort of poster childs for advocating for mitigation. Okay, so the big take-home message is many low-lying coasts and cities are going to be exposed to these more frequent extreme events. Some places could become inhabitable in relatively near-term future. It sounds really grim, and this is what I'm going to end on, is that to me, when I go back and I read the summary for policymakers, it sounds pretty bleak, right? We've got the oceans are absorbing all this heat. We have these marine heating events that are causing major ecological changes. The oceans are becoming acid. I'm telling you, sea levels rising. It's going to continue to rise. Okay, but you know, we need to just kind of step back and think about this, and that is that there's a big difference, particularly in the longer term, between the blue curve, the heavily mitigated emission scenario, versus something more extreme like RCP 8.5. And I will end it there with just sort of one caveat. And this is something that Julian really made me reflect on. Okay, what's really missing here? And what am I not satisfied as an author of the report on how things were laid out? And I think another really important take-home message, particularly when it comes to sea level rise, is sea level is really special in that, and I'm just going to go back to this figure, is that you can imagine that if we have like fringes of Antarctica or Greenland where it's in contact with the ocean begin to retreat back because we're losing these ice shelves, the ice shelves are not going to reemerge and come back until the oceans someday in the future cool down enough to let the ice shelves regrow, to let these grounding lines march back out into the ocean. So the sea level that we're talking about here is like on a reasonable human timescale, it's permanent, it's millennial, it's longer. And some people would advocate that it's not going to go back down again until we literally go potentially, for example, into the next ice age where the oceans really cool down again and we're able to regrow these buttressing ice shelves. So there's a permanence here and a commitment that doesn't apply to all the different systems that are reported on in the SROC, other systems of the climate system. Okay, thanks. I'll stop.
So we'll go on to the next speaker then. Thank you, Rob. Yes?
Question from the stream.
Okay.
So, Joe asked if it was possible to get a comment on specific predictions for the Baltic, because it was hard to see on the figures just presented.
I think we'll take that later then. We don't have time for questions now. So the next speaker is Gustav Hegelius, here from Stockholm University, and he's a lecturer at the Department of Physical Geography, and particularly working on permafrost and the carbon cycle. He's also a leader of the International Permafrost Association in this project for the carbon budget interest group there. And so, yeah, please, Gustav.
Thank you. Yeah, so now me and permafrost, snow cover, and the carbon cycle is what's standing between you and the coffee break. So I was not a co-author of the SROC report. sent my presentation, my slides to a few of the co-authors and gotten feedback, but this is my interpretation and overview and perspectives. So I added some of my own perspectives on SROC's findings. So I just start with this quote from the report: "The polar regions will be profoundly different in future compared with today, and the degree and nature of that difference will depend strongly on the rate and magnitude of global climatic change," which is, there were some of these quite nice and strong statements in the summary for polar makers that really takes this home for us. I also borrowed this graph from the SROC. I tried to, I should use the pointer. I tried to refer to the figures here so you can go back and find the figures in the report. But I like this. This is sort of an artistic view of the terrestrial Arctic system. So now we're not talking about the ocean anymore. We're looking at the land, and these numbers correspond to some of the different aspects that the report touches on. Now I bolded the ones that I'm going to talk a little bit about, which is permafrost. It's going to be the main topic, also reflecting my background. Ground ice, which, so we're talking about the cryosphere. It's ice, but this is ice that's in the ground as opposed to in glaciers or on the sea. Abrupt thaw processes, which is something that affects permafrost. Tundra ecosystem, shrubification, so the shrubs moving in, touching a little bit on the boreal forest, and I will also briefly mention seasonal snow cover as well. I'm actually going to start with really summarizing the key take-home points, and then I'm going to go into more detailed discussions specifically about the permafrost and the carbon cycle, starting with the high mountain regions. So this is chapter 2 of the SROC. There was one chapter on the mountains, one on the polar region. So I sort of broke out and looked at the permafrost and snow in both of these regions. So one strong finding. So this is the really, the take-home messages that you also find easily in the summary for policymakers. Snow cover duration has declined in mountain regions, roughly 5 days per decade in the last 5 decades or so, which is quite a lot. There is an increase in permafrost temperature and loss of ground ice. Not strong statements about loss of extent of permafrost so far or area in the mountains. Very clear signs that species composition and abundance have changed markedly in high mountain ecosystems in recent decades. And also quite strong and clear statements regarding declining snow cover impacts on freshwater runoff to rivers, downstream agriculture and tourism, which we'll hear more about later today. Another really important thing here is that the cryosphere decline in general, including both permafrost and snow, has been observed to increase the frequency and magnitude of natural hazards when it comes to mountain regions. For instance, when it comes to permafrost in mountain regions, the natural hazards are really a concern there. Now shifting gear to the polar region, so looking mainly at the Arctic, but also the Antarctic to some smaller extent. Really dramatic reductions in Arctic spring snow cover extent observed and projected to continue. I'll show a little bit more about that. Frequency of Arctic fires that is observed now and projected for the close term is unprecedented for the last 10,000 years. Really strong increases in the recurrent rates of fires in the Arctic. Strong statements that permafrost is warming rapidly and thaw is projected to accelerate in this century. All these statements with high confidence. Also quite high confidence in the statement that by the end of the century, permafrost areas will decrease by something between 2 to 66% for RCP 2.6. That's a low emit, something that puts us under 2 degrees global warming, and somewhere between 30 and 99% for a high emission scenario, RCP 8.5. And this very wide range here, the large spread, reflects the uncertainty in Earth system models that we have available to project this. So these numbers, basically there's high confidence that it will decrease, but how much, the models still spread a lot. Also statements that present-day losses of permafrost carbon are uncertain. So are we seeing these losses already today? The report says that this is uncertain, but it does say that large losses are projected. So by the end of the century, there is a high confidence statements that we will lose a lot of the carbon that is currently frozen in permafrost, and I will talk a lot more about this. This could release tens to hundreds of gigatons of carbon to the atmosphere for a high warming scenario. And hundreds of gigatons of carbon, those are really massive emissions. 10 gigatons of carbon is roughly 1 year of human emissions today. And another important and strong statement, which I'm not going to talk so much about, but when permafrost thaws and the ground collapses, you also have problems with infrastructure, the people that live there that depend on this ground to remain stable. So by 2050 already, 70% of Arctic infrastructure is believed to be at risk from permafrost thaw. So these were the summaries. So I'm going to delve into more of some of these points for the rest of the talk. This graph shows observed spring snow cover. So let's see. I don't know how to actually get the pointer up here, so I can't point there. There you go. Yeah, that's not working so well. Okay, so I'm just going to skip the pointer. This graph shows a 5-year running mean of the snow cover extent anomaly over the polar regions. The big spread in the early part of the observational record just reflects a spread in 5 different data sets used to observe this. The strongest decline is really towards the end of the season in June, which is still spring in the Arctic, and there's a 13% decline per decade in June from the late 60s going up to present day. And if we project this into the future, you can see a really, the trend the decreasing trend continues unabated at RCP 8.5, the really strong warming scenario, but there is a lessening of the decline with a low emission scenario. So there's again clear evidence that rapid mitigation that puts us under 2-degree global warming makes a very big difference for this part of the cryosphere. Okay, going from snow into permafrost. These are some typical pictures showing you what permafrost looks like. And I myself am sort of a permafrost field researcher, so this is the environment that we go out into. Permafrost is defined as ground that remains frozen all year round. This includes, of course, soil, but it also includes organic matter. So this is a chunk of frozen peat, so it's all old plant remains that are frozen, part of the permafrost. And here you see very ice-rich grounds. All of this that you see here is just massive ice. Also part of the permafrost system, and a very important part of the permafrost system because it really dictates the vulnerability to rapid warming. At present, permafrost covers roughly 20 million square kilometers. That's the area of the whole European Union times 4. Most of it is in Siberia, then Canada, Alaska. We have some in Europe as well, and Greenland, of course, but most by far is in Siberia. And also another important aspect, which actually touches on what Rob said before, is that most permafrost is many, many thousand years old. So if we lose this now, it's not going to be reformed at the policy relevant timescale, especially the ground ice can be 50, 100, 200,000 years old. It's really old systems that we're affecting here. And the main reason why the permafrost is so important it's also important for local indigenous people and ecosystems and all of these other critical aspects of the system. But the main reason why it's gotten a very big policy relevance is the permafrost carbon feedback, which is basically as temperatures rise, partly due to human emissions then, the permafrost will start thawing, and some of this carbon that's in there that I showed, some frozen carbon, will start to be decomposed by microbes, and they release either carbon dioxide or methane into the atmosphere, which further increases the feedback. So it's a positive feedback loop that just exacerbates climate warming. And to put the importance of the permafrost carbon feedback into some sort of context, this is a bubble plot that shows the active pools in the global carbon cycle. So think of the whole global carbon cycle, all of the carbon that's circling around and that we're adding to and with our emissions. The sizes are equivalent to how big they are roughly. Today the atmosphere is more than 800 gigatons. Pre-industrial, it was about 600 gigatons. Vegetation, all plants on Earth, is about 500 gigatons. And soils, so below ground carbon is by far the biggest store here, 2,500 gigatons of carbon. And a big chunk of that is in the permafrost. So somewhere between 1,400 and 1,600 gigatons of carbon is in the permafrost region. Not all of it is frozen. Some of it thaws every summer and refreezes. But these are huge amounts of carbon that can potentially, that are vulnerable to destabilization. So that's the context of why the permafrost carbon feedback is getting a lot of attention. So now I'm zooming back a little bit to findings from the SROC, where they did a lot of work trying to summarize the state of knowledge of permafrost today. So this is Alpine permafrost loss. And here there are no strong statements on areal reduction in the area of Alpine permafrost, and that's just because the models that can project permafrost globally, they are not high resolution enough to really resolve the mountains very well. So this is summarized with observations from boreholes and measurements. And it's subdivided into, here they show the Alps, European Alps, Scandinavia, High Mountain Asia, which is on the Tibetan Plateau. And you do see there's a large variability in the trends. In some areas we don't see a lot of warming. In others, you actually see in Scandinavia where we have crossed from permafrost into a disappearance of permafrost, which might be, for instance, northern Sweden or Norway, where permafrost is thawing rapidly. And you also see some systematic differences between permafrost in debris, so in loose soil, or in bedrock. But clearly permafrost is warming in most places, and there are also strong statements to this effect. One thing that is important to keep in mind here is that there are quite limited carbon cycle feedbacks from the Alpine systems. But the Tibetan Plateau is an exception there. But still, the Tibetan Plateau is about 20 gigatons of carbon, so it's not one of these huge carbon pools that are affected. But I would argue that the main risks are perhaps with this Alpine permafrost instead, ecosystem changes, perhaps changes to hydrology. But for humans, we also have a lot of risks associated to natural hazards, which are really important, for instance, in the European Alps. And I just chose to exemplify this by a very striking picture of a debris flow that was triggered by permafrost thaw that actually overlayers a glacier in this case. So it looks very dramatic. But this is just an example of how collapse of Alpine permafrost can destabilize the Alpine environment, and it causes landslides, debris flows, and other things that can impact infrastructure. If we look at the poles, so the polar permafrost warming and loss, and now we're focusing really only on the Arctic. There is permafrost in Antarctica, but it's very limited in extent compared to the Arctic permafrost. So the rest, when I'm talking about the polar areas, I'm really talking about the Arctic system. From 2007, but between 2007 and 2016, the really cold permafrost warmed by 0.4 degrees. This is based on very solid observations from borehole data, which is for a high rate of warming, which actually exceeds what a lot of models would have projected for that time span. And if we look at projected permafrost area change, we see losses. Here you see the historical losses, and then you see the projected losses start to diverge a lot around the middle of this century, and the difference between 2.6, a low emission scenario, and 8.5 is really massive. It's either we lose something around 4 million square kilometers, or we lose roughly half of the permafrost area already at the end of this century. This is near surface permafrost. There will still be deeper permafrost, but this is the near surface permafrost that will also interact with the carbon cycle up there. And another nice paper that illustrated this for stabilization. So this is permafrost area for different degrees of global warming, sort of stabilization temperatures. So this is the pre-industrial, the baseline temperature +1 is roughly where we are now. And then going down to +6 global warming, which is extremely high global warming, where essentially the permafrost would be gone. So this is depressing, but I think you can also try to look at it in a positive way. It's like if we can also take out from this graph that stabilizing at plus even 1.5 rather than 2 degrees saves 2 million square kilometers of permafrost. So the curve accelerates rather quickly, or it steepens rather quickly, and rapid policy implementations does save a lot of the permafrost. So it's not the trajectory we're on is not completely irreversible, even if we are committed to additional loss. Now I'm showing you a very simplified carbon cycle of an area that has permafrost in it. This is just to illustrate some of the complexities that were highlighted in the SROC regarding how we figure out what is happening to the carbon cycle when permafrost thaws. So we have carbon coming through photosynthesis from the atmosphere. The blue arrows are cooling feedbacks or cooling arrows, and the red arrows are sort of warming the system again. You have the vegetation carbon stock. Some of the carbon is respired by the plants, some of it goes into the soil. You have a soil carbon stock and a permafrost soil carbon stock that are both pretty big, much bigger than this. And some of the carbon that goes in here is also respired by soil organisms growing in or living in the soil, goes back up. But this arrow is smaller than that one. So there's still a net sink in this system. Now, if we make the climate warmer, then all this carbon cycle is just, it's all intensified. So you have more carbon being absorbed through photosynthesis, the trees are growing, you have 2 trees, the carbon stock is increasing, a plus there, more of it is being respired, more of it is going into the soil, and here it starts to become, here the models and observations start diverging. It's the balance here between how much is respired, how much is going in. So so a lot of models do predict that the near surface soil carbon stocks will go up while the permafrost soil carbon stock will go down. And this affects, of course, the amount of soil carbon that is going back, that is being respired up. And there's a, this is a really tricky balance to get right. And this is also reflected in some of the statements that this is still uncertain, which are made in the SROC. This figure now summarizes this, the loss of permafrost soil carbon stock as estimated for the whole world. How much, if we focus just on the loss of old ancient carbon from the permafrost, basically, how much are we going to lose? And this shows going from a really early study and expert-based assessment through intermediate complexity models that are older, a new synthesis of data, and some data-constrained models. This, I would argue, is sort of state of the art when it comes to estimating this part of the loss from the system. And we have moderate emissions and high emissions. So we see basically we just need to take home that there's a lot of spread here. Earlier estimates were perhaps higher, and then data constrained models are pointing towards more constrained losses, but still very significant losses on the order of 50 petagrams or 100 petagrams or so by 2100. So it's very substantial losses still. But when you include models that also account for this complexity of the greening, of the increased vegetation uptake and perhaps new soil formation at the surface, you get a more complex picture. So these models that are coupled also to the vegetation carbon cycle, they actually show, some of them actually show us having a stronger sink, while others have a really strong source. And here, over here, we have a permafrost carbon model into comparison, where the state-of-the-art models did the test together. And basically, the ensemble mean said it's going to be a source at very high emissions, but perhaps even a stronger sink at moderate emissions. So there's a high level of uncertainty remaining in these models. Now, so which is, okay, this might be good news then, but part of the bad news for those of us working with it, that we know that these models actually are missing a lot of the components that they would need to really estimate the full losses of the permafrost carbon. They are still, even if they're state-of-the-art, their system models haven't really caught up to the sort of field-based knowledge and some of the other studies that are coming out. So probably this is a bit of a too positive a message. But what the models are simulating and what is being observed, for sure it's happening, is an Arctic greening, increased vegetation productivity due to warming climate and increased CO2 levels in the atmosphere that the plants like. CO2 fertilizations, they just grow better with more CO2. So this shows Arctic greening over North America. You also see the browning spots, which are almost in all cases fires. Increasing of the fire cycle that leads to this. But if we zoom in then on these models and how well they are able to capture this and how well they are not able to capture it potentially. This figure comes from the paper that is the basis of this summary, McGuire et al. In PNAS, a really nice paper. But one of the things that we can see here is that this graph just illustrates how much the models do spread on different type of mechanisms. So the baseline response of models to changes in CO2 and warming varies dramatically. And here you see some models really take off as a CO2 effect on vegetation, and one model is also particularly sensitive to warming and a warming effect on soil loss, which other models do not have. And this is really a remarkable spread between the models, and it really points us to it. We can't, they are not certain enough in really estimating these feedbacks yet. And some of the potential factors that are not included to the models include nitrogen limitation of plant growth. They don't have a nitrogen cycle in them. Drought losses and fire losses that are also not well implemented. And when it comes to this, the warming effect on soil loss, they also don't include early winter, sort of winter emissions well enough, increases in fire, or abrupt thaw processes, which are localized processes that happen really fast that the models don't have yet, which is what I'm going to come in. I'm going to come into that in a little while. So some of the another take-home message that came from the report is that the present-day tundra is a sink during the growing season, but if you include the winter fluxes, it actually shifts to a source. And this is something that is relatively new. This first paper is already from 2013, but basically what it shows us is the winter fluxes are key, and they actually push the system from a sink to a source. So if you look only at the growing season, that is not enough. We need to also measure in winter. And actually a paper that came this week, I think, which is just published after the cutoff, shows very clearly that winter times fluxes are prevalent across the southern permafrost region and fully offset any summer greening and then some to that. And this is really not represented in the model. So this is new data that has come out very recently. And another of the important processes that we don't have in the models yet is this abrupt thaw. When you can have collapse of, this is a coastal cliff, it's very dramatic, that's why I chose it. But you have different types of abrupt thaw processes happening. And after that, the ground looks like this. It's wet, it collapses, and this is because basically the ice in the permafrost. This is 100,000 years old, this ice, and when that thaws, the ground collapses, the ground surface subsides as the ice disappears, and you get this afterwards. This is what you had before, and it goes from being a carbon sink to a carbon source because of this. This is also something published after the SROC cutoff, partly in review still, and it basically shows that combined abrupt thaw effects almost doubles the radiative forcing compared to the Earth system models that we saw before. So I'm not going to get into the details so much, but this is methane and carbon dioxide. So these are things that were not accounted for in the broad Earth system models. They don't yet have these processes. And just a final slide before the conclusions to show that the abrupt thaw is happening very rapidly, and it's triggered by extreme events. One warm summer can be enough. So 2 papers that came out this year, that documented such event in the Canadian Arctic. So in really cold permafrost, it went from this to this. And this is something that the models say shouldn't happen for another 70 years, but it's being observed already in these summers. And these are also these abrupt thaw processes that are not as of yet in the models. So, concluding remarks, summarizing all of it. Snow cover has decreased and the trend is projected to continue. And losses of snow impact ecosystems, people living in alpine and polar regions, and downstream water availability. Permafrost thaw, warming and thaw is observed and also projected to increase. And this causes losses of previously frozen carbon, and wintertime fluxes and abrupt thaw processes are very important here, particularly important and unaccounted for. This permafrost carbon feedback is something that also, it happens over a long time. This is also irreversible in the sense that it will happen for multiple centuries and millennia potentially. And it responds to greenhouse gas emissions made today, and these feedbacks are not included in the baseline numbers that are used to negotiate naturally determined contributions on the COP21. And also the final, slightly more positive one is that rapid human emissions drastically reduces losses of snow and permafrost, or at least the projected losses, as well as long-term carbon losses from permafrost, meaning that there's still space to very much reduce these losses and impacts on this part of the cryosphere. Thank you.
So is there any question? Okay, thank you. So now we have a coffee break, and so let's resume here at 3:30. So that's 5 minutes later than according to Roma, but 3:30 we'll come back here.